All right, so today we are looking at PFT 118's day 5, which is covering NASM's chapter 2. We call this Basic Exercise Science, which is just the title of the chapter. It's really much more about human movement science than anything. We are going to be working our way through the kinetic chain today. So purpose of today's lesson is to provide you guys with fundamental knowledge when it comes to not only just the definition of the kinetic chain, but also its structure and function. Understanding that basic anatomic structures will allow you to kind of have an insight into how we actually move and how we actually operate and things like that. So after this presentation, our job, if I do my job well, you guys will have a pretty good understanding of the nervous system, the skeletal system, and the muscular system all coming together with a little bit of help coming from the endocrine system as well, although the endocrine system is not part of the human movement system, not part of the kinetic chain, but it does kind of work with the nervous system to kind of control stuff. So we'll talk about it briefly, but and we'll talk about how these systems all respond to exercise. What are the positive benefits of exercising on your skeletal system? What are the positive benefits in your nervous system, muscular system, obviously, right? So when I say human movement system, and what I am talking about, like if I'm talking about how our bodies are designed, like you've got all kinds of different systems running throughout your body. You've got your vestibular system, which is in charge of like helping your balance. You have got your cardiovascular system, which is responsible for delivering nutrients and oxygen and things like that throughout the body. Respiratory system, which is responsible for gathering that oxygen from the environment. So there's a lot of systems that sort of all come together, with like multiple pieces, right? Your respiratory system is, your lungs, but also the passageways. Your cardiovascular system is your heart, your blood, and your blood vessels. Well, when it comes to human movement, every movement we make is under the control of we call it kinetic chain, or sometimes we call it the human movement system. And it's three interdependent systems that all work together to actually produce human movement. So we talk about the nervous system is controlling everything, and it's manipulating the muscular system to contract, and that contraction causes it to drag around the skeletal system. So the reason we use kinetic chain sometimes is because it really kind of paints a picture. It's actually a really accurate descriptor of what this system is, right? It is, if the word kinetic stands for meaning movement and forces and things like that, well, think about what a chain is, right? It's a series of links all together. And if any of those links are out of whack, it's going to affect the other ones, right? If you have a compromised nervous system, through maybe you've just been doing the same movements every single day. Maybe you've just been, a lot of repetitive actions in your job or something. If you're an accountant or something, you're spending all day in front of the computer, right? You are training your nervous system to get contracted into this one particular specific position, right? So now your nervous system is adapted to this specific movement that you've been doing. It gets really good at that, but it gets really bad at, kind of the opposite of that. And it gets bad at things that are kind of adjacent to that. So it's your nervous system kind of gets trained to be very good at one thing and recruiting muscles in one particular way, when it should be good at recruiting things in a lot of different ways, So then, because your nervous system sort of knows how to recruit things maybe the wrong way, it starts dragging around your muscular system and contracting muscles in a way that, is not conducive to particular movements, This is where, when we talk about clients who have elevated shoulders, right? They spend all day, at the computer or something like this, and it causes their nervous system to just think that this is the new passive position, right? This is where they should just be. And it's well, now if I try to raise my arms overhead, I can't, right? My muscular system can't move the way it's supposed to because my nervous system cannot recruit it properly. Meanwhile, that means that like my bones are probably getting pinched together. The joint cavity has limited space now. Now I'm also putting undue stress on my skeletal system. So if any of these components are out of whack, it will affect the other two components. You pull a muscle, it's gonna affect how your nervous system recruits things, and then your bones are gonna move in the wrong way. Sprain a ligament, same concept, right? So that's why we call it the kinetic chain, is because it is sort of a several links that are all working to produce movement, and they rely on one another. So if we're breaking this down, into little pieces here, we're going to start today with the nervous system, which is actually where we ended yesterday, but NASM likes to go in sort of a different order here. Which is good, because like I like the way they teach this. I think that like they do a good job of setting it up. It's like get the control center out of the way and then talk about moving around, and then we'll talk about like specific movements and things like that. So looking at the nervous system, right? By definition, if you're going to put this in your notes, it is a system containing specialized cells that coordinate signals and, this is the important part, provide a communication network throughout the body. So it's kind of a weird definition when you think about it. It's like, what do you mean it's a communication network throughout the body? It's like, well, if you think about like what a communication network is, right? It's information going in both directions, right? Like, let's say, let's say I'm working on my house or something, right? I've got friends over who are helping me, and I'm unloading stuff from like the truck, and I'm like, I tell one of the guys, it's like, hey, I'm gonna take stuff off the truck and leave it here on the porch, and then that guy is like, why don't you take this through the house into the back? And so it's like, okay, well, like I'm gathering information in one way, and then like my friend relays that information to someone else. That's information going back this way. But then like if that person at the end is like, oh, I actually am in the middle of this right now, I can't do that. That information comes back to me, through the middle person first, and then me, right? Sort of a like, tell so-and-so that I'm doing this kind of situation, right? Well, that's a network, right? That's an interconnected network. How many people do you communicate with every day, do you think? You have like a network of communication within like your everyday life. In the nervous system, it's information about maybe our body position. And then that information goes back as like a motor response. It's like, oh, we're in this position, we're not supposed to be in that position. And so then there's a motor response that sort of fixes things, right? Or maybe it doesn't. And that's where we see dysfunction and overactive muscles and, things like that. So there's going to be two primary components of our nervous system in this communication network. We're going to divide things into two primary sections. You are going to see your central nervous system and your peripheral nervous system. So your central nervous system is your brain and your spinal cord, and that is like the command center that's responsible for all of our decision making. If I go to pick up like a 300-pound barbell, my central nervous system is going to say, all right, we know how much weight that is. That's about 300 pounds. This is how much muscle it's going to take to lift it, right? And it's going to recruit as little as it can because it's trying to save resources and save energy, but it will recruit just enough to get the job done. And it'll hopefully recruit my muscles in the right way so that I don't blow up my back, And then you've got your peripheral nervous system, which is all of the nerves that are branching out from your central system. So if the central nervous system is the brain and the spinal cord, right? And that's the decision maker. Well, obviously, like the decision maker isn't the one doing the lifting, and so that is where your peripheral nervous system comes in. That's all of your peripheral nerves that branch out from your spinal cord. And so like, it would travel down and then like branch off to my arm here. And, eventually like it would zap certain muscles, maybe in my hands or my fingertips to cause things to like move around. So those are your peripheral nerves. That's your peripheral nervous system. And you can remember that because it's around the periphery, right? It's around the perimeter. So like I said, it is a communication network. And when we think about like what our nervous system does, right, what its role is, its job is to gather information about our internal and our external environment. Like obviously, we need to gather info about our external environment as well. Like if I grab these scissors right here and I open them up and this is freaking sharp on one end, like if I were to like slide my hand along it, right, that's gonna damage me. That's gonna create like a cut in my skin, and that's gonna hurt. And now like the sensory receptors in my skin are gonna send a signal to my nervous system saying like, hey, like we just got torn open. So there's information going to the brain, and then my brain's going to go, uh-oh, that's not good. The last time this happened, we experienced damage and it took us, a week to repair and things like that. So what we need to do is we need to stop first, we got to stop doing whatever we did there. Right. And so the brain makes all these decisions. Right. And that's one of the other functions of our nervous system. So it's going to gather information about the internal and external environment. Then it's going to process that information and say, okay, let's do appropriate response here. Oh yeah, drop the freaking scissors, and then it will respond. It'll say, all right, well, what muscles do we recruit to open up the hand? What muscles do we recruit to make this, event occur, right? So if we're breaking this down, the three primary functions of our nervous system here, we are going to see sensory function, we're going to see integrative function, and we're going to see motor function. So sensory function is our nervous system's ability to sense changes in that internal and that external environment. So, sensory receptors might sense that you're touching a really sharp object, right? That's a really good example. Or if you go pick up like a 10-pound barbell, right? A little light barbell, and you're picking it up and you're maybe doing just like bicep curls or something. Sensory function is going to say, all right, well, this is how much this weighs. This is how much muscle we're going to need to recruit. And so sensory information is just gathering info. It's going towards the brain, right? You guys might remember from yesterday, we were talking about sensory neurons, neurons that are traveling in the direction of the brain. Well, those are the ones that are responsible for sensory function. So that's one of the main roles. And by the way, this isn't just your external environment, it's also your internal environment. Let's say you're walking and you start going uphill, right? It's going to take a little bit more energy to get up that hill because you're going to have to recruit more and more muscle fibers in order to work against gravity now. And so what starts to happen is as you're going against gravity, and you're recruiting more muscle fibers, well, those more muscle fibers start producing lactic acid the same way all of our muscles do. And now there's more lactic acid in your blood, and that blood is going to run past your heart at some point. And when you're, and your heart's like, oof, gosh, that's some acidic blood. So then because it knows it's very acidic, what does it do? Well, it brings in oxygen to kind of convert that lactic acid into energy. We'll talk more about that in detail in other classes and stuff. But that means that your nervous system goes, oh, well, or we need to speed up the heart, right? So then your heart starts pumping a little bit faster so that it gets better. And then you start breathing a little bit harder so that we can bring in more oxygen and then deliver that oxygen around. So it's not just your external environment, it is also your internal environment. How does food continue moving through your digestive tract? That's sensory information. Stretch receptors in your digestive tract, once they get triggered, cause like little muscular contractions, and that kind of moves your food around. So that's the first part. We need to gather information about things before we sort of execute responses. And then we also have integrative function, which is sort of choosing the appropriate response, right? This is the ability of our nervous system to analyze and interpret the sensory information that we gathered. This allows for the proper decision making and producing like specific responses. So for example, your integrative nervous system understands that touching something that was really freaking sharp is dangerous and will cause damage to the body. And so it is something that should be avoided. I don't know if anybody in here is afraid of, spiders or anything like that. I grew up working in my parents' pet store, so like spiders have never been a thing for me. But bees are something that I'm super afraid of. Like they just make me really, really sketchy whenever I'm around them. You know, that is because like I remember like when I was a very, very, very little kid getting stung, and just my nervous system just remembers that whole horrendous experience, and I'm just kind of afraid of them now. Like it just kind of bothers me, you know, in the same way that like spiders kind of give you the heebie-jeebies. Sometimes there's just like a little bit of instinct, you know. And so like that is probably something that you know, your brain is sort of saying, yeah, no, that's something dangerous. So what I'm going to do is I'm going to make you really nervous. I'm going to make some adrenaline and some cortisol and some stress hormones. And we're going to go in the opposite direction, you know? So your integrative nervous system is sort of interpreting that in order to like respond. Again, if I grab a 10-pound barbell, sensory information is going to come in and say, yeah, we got about 10 pounds in our hands, right? And then my integrative function is going to go, all right, well, that's going to take this much muscle. And then the information is going to go back in the opposite direction. So the information came in, my brain and considered all the variables and then chose a certain response. And now in the opposite direction, we are going to use motor function. So motor function is your neuromuscular response to sensory information. I should say information. So this is the neuromuscular response to sensory information. So for example, motor units are recruited to contract the muscles that draw away your hand from that sharp object, right? You put your hand on a stove, information comes in saying, holy crap, that's freaking hot, right? And then integrative information goes, yeah, we should definitely move the hand away. The muscles we should recruit for that is the biceps, right? And then boom, I do a little bicep curl, and motor function sort of contracts that. So those are the three sort of primary jobs of our nervous system. Now, all of that comes together because there's information going out and information coming back, and this is constantly happening. We have this physiologic process that is probably, I would say this is probably the most important term of the day. I'd say if you forget everything I tell you today, if you can get a pretty good understanding of this concept, I think we'll be in a good spot conceptually, you know? And this is where we're talking about what is called proprioception. So proprioception is your body's ability to sense the relative position of adjacent body parts, which is kind of a big fancy way to describe proprioception, or even fancier than that. You'll sometimes hear is the cumulative, everything coming together, neural input from all proprioceptors, right? That's like really technical. The way I like to consider proprioception, it's your body's spatial awareness, right? It's your body's ability to understand where it is in this universe that we all share, you know? Like, so for instance, like right now, I got my arms abducted at my sides, right? My arms are sitting out here like this. And so proprioception is where sensory information is going into my brain saying, hey, this muscle is currently at this length, and it's experiencing this much tension, and you know, it's experiencing this much like force pulling down on it, like gravity and stuff, right? And then meanwhile, the same thing's happening in this muscle and this muscle, every muscle in my body constantly sending tons of information to my brain that my brain is interpreting and saying, okay, well, if the deltoid muscle is at 50% of its max length and it's at like 25% of its max tension, that means that it must be in this position right here, right? That's what proprioception is. It's your body's ability to understand where it is in space. And it understands that by understanding how much stretch is on a muscle, how much tension's on a muscle, how much force is being, you know, generated by that muscle, whether it's accelerating or whether it's decelerating. And all of that comes together for us to, like, you know, understand where we are and understand how to make the appropriate movements in response. And this is why if you've ever tried to like do a new movement, if you've ever tried to like, you know, rollerblade or skateboard or do something, even riding a bike the first time, you're like, oh my God, how the hell do I do this? You know, like you're like losing your balance. You're like, ah, you know. But then like, as you get a lot of information coming in, your brain logs it away and it remembers it. And then it's like, all right, well, you know, whenever we tip like this, we need to recruit these little core muscles over here that'll draw us back upwards, right? And if we tilt like this, we need to recruit muscles over here that'll draw us back upwards. And so if you're on that, you know, skateboard or something, you're losing your balance. proprioception is gonna help you kind of gather enough information, get you back to neutral. So, like I said, that's probably the biggest term of the day. Just because like that concept is so relevant for us as personal trainers. Like we are constantly stressing our clients' proprioception because that is going to help them move more efficiently. I always show people, I always pull this guy up because he's a little overly wacky, but Instagram. I think that he goes pretty darn far, but there's this kind of famous physical therapist on Instagram. His name's Joel Seedman. And I've pulled him up a couple times here, but he's working with Jadeveon Clown. Go. Jadeveon Clowney, and check this out. This is so fun. He's got him doing, a lot of like balance, right? He's standing up on one leg and balancing like this. This is giving him maximal proprioception, right? There's information coming from the bottom of his foot, his calf muscle, his quads, his hamstrings, his core muscles, everything like that. So he's getting better at like bracing this specific position. You can kind of see he's leaning just a little bit to the side, but then like he gets his body nice and stiff and kind of gets back to neutral, right? That's developing proprioception. Then you can get into like all this real wacky stuff that he starts doing where Seedman loved to do like just very awkward angled stuff. This is developing maximal proprioception. It's a weird angle to have to lift something at. Generally we see regular old lunges or regular old squats, but doing this kind of, I don't know what you would call this. It's a version of like a landmine lunge, is very awkward. Or look at this version here, right? He's kneeling, he doesn't have a lot of like surface area, and look at how much work his foot's doing, right? Look at how like that's kind of tilting and wiggling side to side, right? That's maximal proprioception. Or look at this nonsense, right? Like he's loaded up on one side and not the other. That's a lot of proprioception. So, I'm not saying you have to do all of those exercises, but when it comes to like training our clients, we at NASM, we do a lot of proprioceptive work. This is why we have the entire stabilization level of our program design continuum. Like when we're looking at the OPT model and we're picking exercises, it's like, all right, well, beginner clients, they're going to get the wobbliest, unstable versions of squats and hinges and lunges or whatever. They're going to get the unstable versions because if they know how to move properly, thanks to the unstable versions, they're going to move really well when we get to the heavy versions of things. If I can do a bodyweight squat on a Bosu ball, I can do a barbell squat without, worrying about my back rounding or something like that, right? So training your proprioception is a really great way to positively, long-term, properly train your nervous system. You're going to learn how to do things the way you're supposed to. So that is sort of the concepts behind the nervous system. Any questions, comments, or concerns so far? Lorianne, Cody, Bay, Gabriel, you guys feeling good?
Yeah, I'm feeling good.
Actually, I got one question. Gabriel, do you prefer Gabe, Gabriel, or any variation? You got a nickname? What do you prefer?
No, Gabriel's fine. Gabriel's fine.
Fine, yeah. Or is your favorite?
It's fine until like, I get to know you, and then you'd be like, Gabe is short for Gabe. It's cool.
Okay, I'll take it.
Yeah.
I like, my name's just Brad, but like right. My middle name is Lee. So like when people call me Bradley, I'm like, nope, that's super not my name.
Yeah. See, you correct them.
Yeah, I always like to call people what they would prefer. Okay, so let's take a look at neurons here. So we're gonna zoom in like crazy. If we understand, there's our concept, right? Now let's go ahead and look at how we do all this. So zooming in here, we're gonna look at some microanatomy. If we're looking at our nervous system, your nervous system is made up of billions upon billions upon billions of neurons, right? So the neuron is the functional unit of the nervous system, right? And so, nerve cells are making up your entire nervous system. And for the record, inside the cell's body, you've got all the normal stuff you're going to see in every animal cell out there. You're going to see a nucleus, you're going to see mitochondria to produce energy, you're going to see lysosomes to clean it out and keep it healthy. You're going to see Golgi complexes to assemble ribosomes and, grow that cell in the direction it's supposed to grow and stuff. But one of my favorite concepts that you guys have heard me say before, that I love to bring up is function follows form. Something needs to look a certain way if it's going to act a certain way. So some of the stuff that you don't see in every type of animal cell, but you definitely see in neurons, you're going to see these special fibers called dendrites around the outside. And these dendrites are like little branches, little fingers that reach up from the body of the neuron. And then you're going to see these big long tails, and those tails are covered with this fatty material, these little beads that you can kind of see here, called myelin, right? And what that does is that makes this cell in particular really good at generating an electrochemical response to stuff, response to stimuli. It's really good at producing electricity. And so we are actually going to zap a neuron, and that electricity is going to travel down this big long tail, and then it'll be connected to another neuron, and then it'll be connected to another neuron, and another one, and another one, and another one, right? And that is where, we're getting information from my brain all the way down to my right big toe, which is not close to my brain. So it's traveling from neuron to neuron to neuron, sort of allowing that to work. And they wouldn't be able to do that if neurons weren't shaped very specifically. So the cell body is sort of the main portion of the cell. It's going to have all the normal organelles that you would see in any sort of classic animal cell, but it's going to have some special sections as well. Like the axon is the tail. This is sort of the communication from the brain and the spinal cord. Like the tail of the neuron is sending information away. So information would sort of come in, let's say I've got another neuron over here, right? Information would go from that neuron, and then it would come into the little dendrites here and be gathered, and then travel down the tail of that one, and then it would grab the next neuron and then travel down its tail. It's where, the real kind of heavy lifting of covering some distance sort of happens, right? So the axon is the tail that's sending signals away, and then dendrites are gathering information from other, different structures of the body, right? They're the fingers that are kind of gathering info in the same way that, like, if you were in the dark feeling around, right, you'd be like, where is that? It's like, oh God, what is that? That's furry. And I was like, oh, it's my dog. Like you'd be gathering information by kind of feeling things out. That's kind of what dendrites do. So when it comes to neurons, there's going to be three primary types. We talked about this yesterday, but you are going to have sensory neurons. Sensory neurons are neurons that are going to transmit what we call afferent impulses from receptor sites. Receptor sites to your brain or your spinal cord, right? So they're going to gather information that is heading back towards the brain, right? So good example of sensory receptors are all of the sensory receptors in like your skin. If you've got like a spider crawling along your leg and you're like, what is that? Like you're going to feel that sensation thanks to your sensory neurons. They're going to be gathering info coming back. You go pick up a barbell that's, again, like, let's say 100 pounds, right? Your sensory information is going to say, hey, this is some, big heavy weight, right? So neurons that are transmitting information towards the brain. And then because your brain is not exactly close to every part of your body, you have interneurons, which are neurons that are transmitting information from one to the next, to the next, to the next, to the next. So your sensory neuron might gather information at like a specific site, and then it's going to pass that information to an interneuron. And then that interneuron will pass it to another one, which will pass it to another one, which will pass it to another one, until eventually it gets all the way up to your brain. And then your brain can do integrative function. It can analyze all the information that it got and say, okay, this is the appropriate response, right? If we are going uphill, we got to recruit the calf muscles this much harder at this angle, and that'll help us like not lose our balance and fall backwards. There's our integrative function. So then your brain is going to choose the appropriate motor response. And so it will then recruit muscles back in the opposite direction. So now from the brain, it's going to travel down the spinal cord and to whatever section it's going through motor neurons. And so motor neurons are neurons that transmit efferent nerve impulses from the brain to an effector site, such as like a muscle or maybe an organ or whatever, right? So, again, if we track like a little bit of information here, right? You go touch something, and so sensory neurons gather the information, and then that information goes from interneuron to interneuron, all the way up to the brain through all the interneurons. Then it travels back through more interneurons, back to an effector site that says, hey, like in response to that information, this is the muscle we choose to recruit. So, moving the bicep, moving the tricep, like whatever it happens to be. So looking at the divisions here, if we're talking about like dividing things down, we are going to have our central nervous system and our peripheral nervous system. Again, the central nervous system is your brain and your spinal cord, and the peripheral nervous system are all these nerves that are branching out from there, right? You can see a whole bunch of them there, all kind of branching out, controlling different sections. This is where if you ever know someone who is like a paraplegic, right? That is because like they damaged this column, this spinal column, and now certain information can't travel down any further. And so that information never gets to wherever it's going, or maybe it's not sensing information coming back, right? Or if you know somebody who's had like a stroke, and it's like killed certain nerves or certain tracts, that's going to prevent like information from being able to travel down specific highways, and there's a lot of different pairs. There's a lot of different structures. We're not going to go over them like too in depth, but yeah, you got 12 cranial ears, you got 31 pairs of spinal curves, that are spinal nerves, not curves, that are kind of branching out from there. And each of them are sort of, happening at all these like individual discs that you've got, your lumbar spine, your thoracic spine, whatever. But they're all providing like different pieces of communication and sensory information to the nervous system. So your peripheral nervous system, the stuff that's sort of branched out around, it's going to divide into two primary divisions. Your peripheral nervous system is going to divide into the somatic division and the autonomic division. And so the somatic division is all the voluntary stuff. When you choose to squeeze your bicep and move your arm, that's a somatic response. Controlling skeletal muscle is very much somatic, right? This is something that you have conscious, voluntary control over. But there's also the autonomic division, right? There's also your heart rate, right? We cannot make our heart rate beat faster or slower. We don't have any control over the pace of our heart. And like, I know that some of you might be going like, well, I mean, like, I could think about something that makes me nervous and it'll speed my heart rate up. It's like, yeah, you could do that, but that doesn't mean that you are consciously controlling it. You don't have like somatic function over your heart rate. I don't care about what monk you've read about on BuzzFeed or whatever. Trust me, nobody has somatic control over their heart rate. It's all, autonomic. It's something that is on autopilot. It's involuntary, right? And that involuntary stuff is either going to speed things up or it's going to slow things down. So autonomic nervous system is going to divide further into the sympathetic, which is the fight or flight portion, or the parasympathetic, which is the rest and digest portion. So if we need to speed your heart rate up, that's a sympathetic response to the autonomic portion of our peripheral nervous system. It's like a little flow chart, right? If we need to slow our heart rate down, that's a parasympathetic response to the autonomic portion of our peripheral nervous system. So your central nervous system is controlling all of this. It's making all of the decisions related to these things, but these are the divisions that are kind of carrying that out, and that's how those functions are sort of working. Now, in terms of like how we got this like really great, like I said, communication network, the stuff that's really relevant to us, right? The stuff that's very important for us as like personal trainers, we've got to talk about sensory receptors. So sensory receptors are, located all throughout your body. You're using sensory receptors right now to look at this screen. You've got the ones in your eyes. These are called photoreceptors. Photoreceptors are picking up on different wavelengths, and that's saying, hey, well, his bedspread is blue and so is his wall and the friggin' painting on there, right? Like it's allowing you to interpret like specific colors and light waves, and that's allowing you to see. those are your photoreceptors, right? Meanwhile, you're also using probably some chemoreceptors right now. Chemoreceptors sense chemical changes. Their job is to, if I've got my morning coffee here with some sugar in it, right? That's going to send information to my brain saying like, hey, there's some sugar and caffeine in this food, right? That's a chemoreceptor, right? Or smell, right? That's another chemoreceptor. It's like, oh man, I don't know what that is, right? Like that's chemical changes. Oh my gosh, I'm sneezing again. Woo. So then you've also got like nociceptors. Nociceptors, these are pain receptors. They actually don't kick on until you hit like a certain threshold of things, right? Like if I were to like, poke something into my palm, it's fine at first. There's no nociceptors being activated. But if that something gets really sharp and all of a sudden I'm like, ow, 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 right? That's where my nociceptors kick on. Those are your pain receptors. So there's a ton of them out there, right? Tons of different receptors running throughout the body. Not all of them are relevant to us. The ones that are relevant to us are what we call the category of what we call mechanoreceptors. Okay. So mechanoreceptors are sensory receptors that sense physical changes to things: touch, pressure, acceleration, deceleration, stretching sensations, right? So for instance, like in your skin, you've got some mechanoreceptors. If you were to like grab your skin and just kind of twist it, you would feel that kind of stretching sensation. And so mechanoreceptors are saying like, hey, like our skin's getting twisted for some reason, right? Like, but more relevant, like I said, to us, are these three primary categories. Now, again, I would say probably the most important information is proprioception, but this is kind of related to how we have proprioception. So the three primary mechanoreceptors that we're going to talk about are muscle spindles, Golgi tendon organs, and joint receptors. Okay, so what a muscle spindle is, it's a sensory receptor. And I'm going to pull up a picture here. It's a sensory receptor that runs the length of your muscle, and it looks something kind of like this, right? You can see it's kind of like a coil that wraps around your muscle fibers, okay? And so this is how your muscular system, which when it's manipulated, is going to send information to the nervous system portion, right? When your nervous system is using this muscle spindle to experience however much tension is in that muscle. And so when the muscle is like stretched out, you can see like, the spindle is, kind of being pulled apart. Whereas like when the muscle is contracted, the spindle is kind of being squished together, right? And so like if you're holding on to something, muscle spindles are sending information to the brain. Let's say like here's a relaxed muscle, right? Let's say this is since it's relaxed, maybe it's like in a lengthened position, but it's not like stretching. Let's say this is at 80% max length. It can expand about 20. You can get about 20% longer if you stretch it out, or it could contract to its maximum like sort of shortness, right? And so actually we'll use 50% as our fake number here because that's in the middle. So when it's relaxed, it's at 50% max length, right? When it's contracted, it's at 0% maximum length. It's fully contracted. And when it's stretched out, it's at 100% max length, right? And so the sensory receptor, the muscle spindle, is sending that information, relaying that information to the brain. So for instance, my deltoid right now, as it's resting at my side, my deltoid is in a stretched position, right? Because, when it contracts, it pulls like this, it shortens this way. And so when that shortens, it contracts and my arm drags my skeletal system upwards, right? So muscle spindles are the ones that sense the length of your muscles. Now, also working together with your muscle spindles to tell your body what position it's in are what we call Golgi tendon organs. And Golgi tendon organs don't live in the belly of the muscle the way our muscle spindles do. Instead, these live in our tendons, okay? So where your muscle is inserting onto a bone. And their job, you can think tendon, think tension. Their job is they are sensory receptors that are located in the tendons of a muscle, and they are sensitive to changes in tension and the rate of tension changes. So the muscle spindle is telling your brain how long a muscle is, and the Golgi tendon organ is saying how much tension there is, whether or not it's going to rip off the bone. When there's a lot of tension, you experience that sort of pain sensation. If you've ever been like, when you're stretching and you're like, oh God, like you're like trying to reach and it kind of feels like right, for me, it's like the hamstrings, right? If I'm like stretching out my hamstrings right behind the back of the knee where my hamstrings are inserting, those Golgi tendon organs back there really sensitive, and so like they're experiencing like they're getting pulled on the bone, right? Well, that pain signal is there to protect you. If you keep pulling on that bone hard enough, eventually you'll rip it off the bone. You're going to pull a muscle. So Golgi tendon organs create a pain signal before that happens in order to keep you from overstretching. So those are sensory receptors that are saying how much tension there is. Right now with my arm resting here, the tension's pretty low, right? But if I had like a lot of weight and it was dragging my arm down, maybe the tension would be a little bit higher. And then there's also joint receptors, which there's actually like joint receptors actually have specific names, but we kind of lump them all together because they all kind of function as a group. And so joint receptors are sensory receptors that live within your joint, and their job is to sense pressure. If your joint is being squeezed together, their job is to sense acceleration or deceleration, like how fast a joint is moving and stuff. So those three things are coming together to make up your proprioception, right? Like if I told you that the bicep muscle in my arm is at 50% of its max length and it's at, relatively low tension. Meanwhile, my deltoid is also at about 50% max length and also relatively low tension. You would say, okay, well, deltoid at 50%, if this is its fully shortened and this is it fully lengthened, 50% would be here. And same thing is true of the bicep. If this is fully lengthened, this is fully shortened, 50% would be here. You could actually kind of figure out what position I'm in. If I were to like give you a map, I would say like, all right, I've got a person and they are at 50% here, they're at 75% here, they're at 20%. And you could honestly like figure that all out and say like, all right, well, it sounds like they are in the bottom of a squat, luckily your nervous system is a lot better at this and doesn't have to necessarily just, use a little bit of Simon Says to kind of figure that out. Your nervous system is constantly getting all this information. So here's the thing though, with all of that, it's, understanding our body and what position it's in and stuff, it is pretty easy to misinterpret that information. It is pretty easy to alter your proprioception. If you take a muscle and you shorten it all day, and you leave it in that position, right? Let's say you elevate your shoulders. So right now, like I'm rounding my shoulders, right? Because my chair is kind of pushing me forward. So if I spend all day like this, when I go to stand up, my Golgi tendon organs and my muscle spindles, which are there to protect my body, are going to say, whoa, 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 whoa. If you go back here, you're going to overstretch. So they start to become overactive. So then they create a little bit of like tension, a little bit of pain signal or something, a little discomfort that says, no, go back to this position. We were happy in this position. We knew this was safe. And this is where our body gets used to doing particular movements in particular ways. This is why we have bad movement patterns or bad habits when we try to do like specific exercises and stuff. So that rounding sensation, my body gets used to that. And now all of a sudden there's overactive muscles in my pecs. So I need to stretch those out to restore my proprioception, and that's why we use stretching techniques to do that. So, you're definitely going to see people improve. You're going to start training people and they're going to get better at stuff pretty quickly. Actually, it's always kind of fun to see someone, improve even just between like set 1 and set 2. And those early improvements are not because like they've put on a massive amount of muscle, like they're like, at first 20 squats will be really difficult for someone. Right. And then, they're like, what, this is easy. Let's do 20 squats while I'm holding onto a, a kettlebell or something. Like, yeah, heck yeah, let's do that, and they got a little bit better at that particular movement. And so those early stage improvements are often not so much because you're gaining muscle, but because you are developing your nervous system. Your brain is getting better at these particular movements. And for those of you who were in last mod, so Lorianne, Cody, and Bay, you guys might remember we talked about one of the things that kind of explains why our clients hit a plateau is because their body gets used to things. They burned a lot of energy doing those squats when they were doing those squats inefficiently. When they were doing them a little bit wrong, they burned a few more calories because they had to recruit muscles to kind of stabilize. And so this sometimes explains why our clients are like, I don't get it. I stuck to the program. I haven't fallen off the wagon. I did everything I was supposed to do. Why am I not losing weight? And it's like, well, the bummer is the better you get at all of this stuff, the less calories you burn doing it. Like walking is not hard anymore. I mean, or at least that's what people are supposed to say. I disagree. I think that walking is just as hard today, or if not harder than you were when you were an infant. In fact, yeah, I can definitely say walking is way harder now than when you were a baby. You weigh so much more than you did when you were a baby, but you're really good at it at this point. So it doesn't feel like it's harder. It feels like it's incredibly easy, Same thing is true the first time you ever try to run a mile or, lift 100 pounds off the ground. Those things feel really hard until your nervous system, your muscular system, your skeleton gets used to those movements. All right, so that's the nervous system. Those are all the most important parts of that. Any questions, comments, or concerns before we move into the bones?
All good.
Love it, love it. All right. I'm seeing nothing but thumbs up. All right. So let's take a look at the skeletal system here. So skeletal system is the framework of the body. It is, responsible for giving us structure. It gives us these big long levers that we can manipulate for movements and things like that. And it protects certain parts of the body, right? And luckily, this skeletal system also comprises of all of our joints where these bones are coming together. And so those are manipulation points, right? Those are positions where we can move stuff around and, manipulate things a lot, right? So there's going to be two primary divisions in the same way that there was two primary divisions for our nervous system, central and peripheral. You get two primary divisions of your skeletal system as well. You have got your axial skeleton, which is your skull, your rib cage, and your vertebral column. So that's protecting a lot of your delicate organs. And then you've got your appendicular skeleton, which is your arms and legs. So you can kind of see those two primary divisions right here. There's the arm attached with like our collarbone there. There's our leg attached with our pelvis there, right? And so those are the appendicular portions. And then the axial stuff is all along, the middle there. So your bones are, these big, hard, long organs that act as levers to be manipulated by our muscular system. So thanks to, if I want to be able to reach something that's over here, I got this big long bone, and when I recruit my deltoid muscle and pull it this way, it drags that bone around. And so bones are the actual levers whenever we're talking about like human movement. And your bones are alive, they are, a lot of times we think of them as like this kind of dead tissue living inside of our body, but that's not really true. They're made up of proteins, and there's all these cells that are constantly repairing those bones. They are 100% like living tissue. And so because of that, when we're talking about like, developing our bones and growing our bone density and things like that, we've got to talk about this process called bone remodeling. So bone remodeling is the process of constantly breaking down old bone tissue and repairing it to build up new, stronger bone tissue. And this is something that we do consistently whenever we exercise. Exercise is putting stress on those bones. Imagine, again, if I'm doing lateral raises, right? If I've got dumbbells in my hand, I'm doing this, right? This big, long bone, this big lever is experiencing flexion, right? Like it's bending a little bit when it's held end to end. And so that might create like little tiny microscopic fractures inside my bone. We were looking at this. I pulled this up in the evening class. Let's see here. Bone tissue. This is going to be, I hope I get the right picture again. But when you look at bone tissue, you know, it's all these little tiny pieces here. I think it was this one. Oh, maybe it was. Oh, no, there it is. You can actually see a little fracture here. Now, obviously, when I say fracture, I don't mean this is a broken bone. You know, this is a microscopic little tiny imperfection, right? So that little tiny microscopic imperfection of all of this calcium and all the proteins that are running throughout all of this is going to need to be repaired. And so I've got these specialized cells that are responsible for repairing it. And those are going to be your osteoclasts, which are these special cells that actually eat away old or damaged bone tissue. So what's going to happen, you can kind of see there's a little ridge on both sides here. Osteoclasts might come along and kind of eat away this portion of the bone and kind of, you know, break it down. And then I've got these other muscles that are going to work with the osteoclasts called osteoblasts. And they are specialized cells that are going to build up new bone tissue that's going to make it a little bit stronger and a little bit more resistant to damage in the future. When you're a kid, your osteoblasts, your bone makers, are super, super active. But as we get older, our osteoclasts become more active and we start breaking down bone tissue more. And this is one of the reasons why it's so important to exercise, especially, you know, into seniorhood. You know, we definitely want to stay very physically active because that's going to ensure that we are, you know, signaling to our body like, hey, like I'm breaking this bone down. I use this stuff every day. And so your body will have a physiologic response of building that bone tissue back up rather than breaking it down. So those are your osteoclasts and your osteoblasts. Now, looking at the different types of bones, you guys don't have to have too much of this memorized in this course, by the way. This is going to come up. This is much more of like, similar to like our joint movements and things like that. This next section that we're going to talk about, it's important and it's in chapter 2. But we definitely spent a lot more time breaking this down and understanding movement next mod in PFT 119. That's our kinesiology class. But just briefly touching on this right now, we do have a couple different types of bones. They are named after how they look. Here's a long bone. Long bones are long. You've got short bones. Short bones are short. They're sometimes referred to as cuboid bones. You'll sometimes hear that. And those are like, you know, like the carpals in your wrist, right? The tarsals in your ankle. You got flat bones, which are really thin and kind of protective. And then it's like scientists ran out of names and they couldn't figure out what to call the last one. So they just called them irregular bones, which are the weirdo ones. You know, irregular bones are very uniquely shaped. Your spine, for instance, has all these like, you know, big processes that are kind of branching out from them. And that allows like little tiny muscles to kind of, you know, grab from here and then like reach down and stabilize, you know, these little like transversus spinalis muscles, you know. And that makes them really good at like creating stability. But at the same time, like we need to be able to like, you know, rotate around. And so you're going to have oblique muscles around the outside of that, you know. And so there's a lot of attachment and there's a lot of like, you know, soft, delicate structures in this area. Irregular bones have irregular shapes so that they can kind of facilitate that. Now on your bones, you're going to have some really cool indentations and markings and stuff. Your bone markings are going to be, we call them flattened or indented portions of bones. This allows muscles to get a really good grip. You know, you look at this big ridge right here. If I were laying a muscle on top of that, like my supraspinatus, and it ran, you know, lives on the top of this ridge here and then circles around, it's going to grab my, you know, humerus over here. Just like that. And so it's going to run like this. And that's the supraspinatus muscle, you know, which is a stabilizing muscle in your rotator cuff. And so it has a really good grip thanks to the bone markings. You know, you're going to have what are called fossas. You're going to have processes, you know, lots of different like really cool kind of interesting shapes. Processes, for instance, you know, you can see here this little projection from the bone rather than like a dent, which, you know, is a depression. This projection here, we call that a process, right? And so lots of really cool markings, around our bones that are allowing our muscles to get a really good grip and kind of, or connective tissue like ligaments and things like that to get a really good grip and kind of manipulate things and move them around. There's your vertebral column, by the way, several sections of vertebrae. You can see your cervical vertebrae at the top, that's your neck, your thoracic vertebrae, which is your upper back, your lumbar vertebrae, which is your lower back, sacrum, which is attaching your pelvis together, and then your tailbone at the end, that's your coccyx. And, like I said, your nervous system is going to run through this, all this hard tissue is going to keep that protected. And then, your peripheral nerves are going to branch out from there. So those are that's a general guide to the bones in the body. Now, obviously, if we're talking about bones, we also have to talk about joints. Joints are, where one bone is sort of or articulating with another one, right? Where two bones are sort of meeting up, and that's where a lot of this pivoting action is going to take place. So there's a lot of different types of bones we're going to see, or types of joints, but we're going to see three primary types of joint movement. You'll sometimes hear this referred to as arthrokinematics. Arthro means bones, kinematic means movement. So, arthro means joint. Kinematic means movement. So this is literally joint motion. I don't know why we need that word. That word is literally longer than the definition, but whatever. And so there's sort of three primary types of movements that are going to happen in our joints. We're going to see a rolling joint action, which is where one joint surface rolls across another one. We're going to see a sliding joint action where one joint is sliding across another one. And we'll see a spinning joint action where it'll spin about its axis, right? So if we look at the knee, for instance, let's see if this works. Oh, come on, internet. So you can actually see there's a little bit of sliding that's happening there, right? So that's a gliding action, but at the same time, there's also a little bit of rolling that happens at the end. So that's a rolling and a gliding joint action. Then there's gliding, happening up here up top, right? But you'll also notice this is kind of moving a little bit laterally, right? It kind of starts off to the side. Your kneecap kind of sits a little bit more medial, and then it kind of slides into this groove. So there's a gliding action there, but that's a little bit of a twist. So that would be a spinning action. So those are kind of like every bone in your body really does this. Actually, there's a really good picture of the patella and how that kind of sliding and rotating occurs simultaneously. You can see it kind of moves off to the side there. And so, that's all three of those actions kind of happening simultaneously. So those are the three sort of main types of joint movements. Now, if we're classifying our joints, here's the thing: not every joint is designed to actually move around a lot. We're going to have two major classifications of joints. We're either going to have non-synovial joints or we're going to have synovial joints. When you think of a joint, you're probably thinking of a synovial joint. Those are fully movable joints. When we think about how we're manipulating things around, we think of joint pain because maybe there's instability or something. That's very much like happening in synovial joints. Non-synovial joints are either not movable at all or only semi-movable. So for instance, like the sutures of your skull where several skull bones are coming together, we don't want that moving around. So that's a non-movable fibrous joint. But then, if you look at where your two pelvic bones come together, that's a really good example of a semi-movable joint. It can do a little bit of movement like this, a little bit of this, a little bit of this, but it's not really designed to do a full freaking range of motion. That's where your synovial joints come in. So synovial joints they are fully movable joints. They have a big joint cavity that allows enough space so that there's plenty of movement that it can occur there. And then they're also producing synovial fluid, which is this kind of grease on the inside of our joints that keeps there from being too much friction. And they will often have other specialized structures that will give them a little bit of stability in there as well. Things like ligaments or, bursa or fat pads or whatever, right? And so you can actually kind of see if we look at like, here's the knee joint again. This is a classic example of a synovial joint. There's going to be a big cavity here. Look at how much space there is between those two bones. A little bit of fat pad right there. There's these little bursa that live under there. And then there's like your ACL ligament. There's your PCL ligament, right? So that's like the soft tissue that's there to provide stability, but also, be flexible enough to provide movement. Talking about our joint connective tissue, and here's a sort of a better picture. Here's I have a love-hate relationship with this picture. This picture's in this PowerPoint twice. They look really similar, but you can see tendons and ligaments. So don't get tendons and ligaments confused, guys. Tendons attach muscles to bones. Ligaments attach bones to other bones. Okay, so this right here, this is the ligament right along the outside of the knee. This is called your LCL ligament. That's your lateral collateral ligament, and it's attaching your femur to your fibula. And it lives right there, right? Meanwhile, you would have like your ACL ligament in the front, you'd have your PCL ligament in the back, and you'd have an MCL ligament that's actually on the opposite side of the LCL. So those ligaments, these special structures that are connecting the bones together, they're great, but they don't repair very quickly. So when you think about like someone spraining an ankle or spraining a ligament in their knee or anywhere really, the reason that happens is because, you could be on like a weightlifting routine. And, if you're like really making strength gains, like you're really getting better, consistently, you're on like a 6-week, 8-week block or something. And you're just like, man, I've raised my 1 rep max by, a substantial percentage. I'm really killing it in the gym lately. But you'll start to feel it in your joints. You'll start to feel like kind of aches and pains. And you need to do what's called a deload week. You need to, if you're really committed to lifting heavy, you need to take a little bit of a break every now and then, because your connective tissue just doesn't repair as quickly. Ligaments and tendons, the reason they're both drawn in white is because, they are kind of like a lighter color. But the reason we always draw them in white is because that's representing very low blood flow. Look at this bright red stuff. It's stained red because of how many red blood cells are running through it, right? This stuff isn't getting as much blood flow. It just doesn't have as many blood vessels running to it, so it doesn't get nutrients delivered as often, so it repairs much more slowly. And we need to remember that whenever we're writing programs and we're taking someone through like a training cycle. If I'm training an athlete, and they're about to go into like the regular season, I'm going to train the crap out of them. I'm going to push them to their limits in the preseason. And then that week before the season starts, I'm going to back off and I'm going to, give their body time to adapt and time to repair. And then during the season, they're working as hard as they can because, they're an athlete. They're leaving it all on the field or leaving it all on the court every single time. I'm going to make sure that, I'm not pushing them. I'm not trying to, like LeBron James is not trying to improve his bench press in the middle of the season. He's not trying to improve his squat. He's not trying to improve his vert, which is hugely important for like a basketball player. But he's not trying to learn how to jump higher in the middle of a season. That's off-season stuff, that's where you improve. You're just trying to maintain so that you can continue working at peak efficiency during the season. So I'm going to take it easy during the middle of the season, and I'm doing that because, if the body could repair, way faster, sure. Yeah. I'll push them a little harder, like if our body could repair so much faster than it actually does, we could do maximum lifting all the time and we would never need to have like training cycles. But unfortunately, that's just not how we work unless you're on steroids. That's why that breaks all the rules. And don't do that stuff because it causes a lot of other problems. So talking about our skeletal system, bringing this all together, we're talking about exercise. One of the best ways to make sure that you are maintaining this skeletal system and you're keeping it healthy and allowing it to move is to do what we call weight-bearing exercise. Weight-bearing exercise is anything that's working against gravity as a resistance. So like running and lifting weights, doing body weight exercises, those are all really good examples of weight-bearing exercise, and they all have really positive effects on your skeletal system. Those are the best ways to improve your bone density. Now, swimming and cycling, they are also working against resistance, but they're working against a different type of resistance. Like swimming is working against like sort of the friction, viscosity of like fluid, right? Same thing with cycling. And I love swimming and I love cycling. They are both very, very good for you. But when it comes to bone density, particularly lifting weights is king. That is really going to do a much better job of developing your bones, developing your connective tissue. And so there's just something special about working against gravity in particular. This is why when we watched that crash course video on bones a couple of days ago, he opens with the story about the astronauts living in space and how we see like 1 to 2% bone loss per month. And that happens because there's just no gravity. And so, you know, our body's physiology is designed to go, well, if we're not using this bone density, I'm going to eat it up, you know? And so it just kind of eats it away because, well, if there's less of you, you will burn less calories and you're technically more efficient. You know, not the type of efficiency we're kind of going for, but, you know, that's sort of what happens. So that is your bones in a nutshell. That's a review of our skeletal system. Any questions, guys? How you five feeling?
I feel good.
Love it.
Good.
Hey, cool.
So good.
All right, cool, guys. This is a nice. I like that this landed on a Friday. Because it's kind of summarizing our entire week that we just went through. This is working well. Send you guys off for hopefully a relaxing weekend. All right, let's take a look at our muscular system. So your muscular system, a series of muscles under the control of your nervous system that are generating internal tension in order to be able to overcome external forces. Right, so they're these specialized organs that have contractile proteins in them, that those proteins are really good at grabbing each other and sliding around. And so muscle cells are really good at going from being this long to being this long and then relaxing back to full length. And so that contracting and relaxing, if that's happening in thousands of muscle cells simultaneously, well, then my entire muscle is going to get shorter. And when that happens, it's going to pull on the things it's attached to. And those things that's attached to are our bones. And so that's going to manipulate our skeletal system. But it needs to know how to do this. So it's all under the control of our nervous system. So if we are looking at the structure of skeletal muscle, right? When we talk about like what a muscle is, if we take a look here, I always pull up the same picture, but it's such a good diagram. You take a look, here's an individual muscle cell, right? So now there's these little proteins within that muscle cell, which you're seeing here. Those proteins are called myofibrils, right? But here's the actual muscle cell itself. And you can see this is bundled together with this one and 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 this one, right? One, two, three. Probably 24, maybe 25. So there's probably like 25 muscle cells in this little bundle right here, right? And so this bundle is all kind of wrapped in this connective tissue right here. And this is called a fascicle. So a fascicle is a bundle of these little guys here, these individual muscle cells. And if you look at like what a muscle cell is, well, it's got all the normal stuff. You can see like there's some nucleuses right there. This is capillaries that are kind of running throughout it, delivering blood and stuff. There's some mitochondria, but the special things, in the same way that neurons had special fibers, bones had special fibers, special fibers within muscle cells are going to be called myofibrils or myofibrils. And they are proteins that have these really cool little contractile elements to them. And so there's a whole bunch of myofibrils all bound together inside of each individual muscle cell. And then that muscle cell is bound together with other muscle cells. And then that fascicle is bound together with, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 other fascicles. And all of that comes together to make up the belly of our actual muscle. So a muscle is a compilation of a whole bunch of individual muscle cells, whole bunch of individual muscle fibers that are neatly wrapped together with connective tissue at every end. So you're going to have a muscle, which is a bundle of fascicles, and a fascicle is a bundle of muscle fibers, and muscle fibers are bundles of proteins called myofibrils. A lot of bundles on bundles of bundles. So here's the definition for each of those, right? Like I said, a muscle is a compilation of all of these muscle fibers. A muscle fiber is an individual muscle cell, and a fascicle is a bundling of muscle cells. And there's that picture again. All of your muscles are going to kind of end. You can see like there's the muscle, bunch of fascicles all bound together. And then that all kind of comes together, starts to get a little lighter in color, and then eventually becomes this kind of collagen-y connective tissue that grabs onto a bone. This is the tendon, okay? So this is your quadriceps and patellar tendon here. And so they're going to provide the anchor point from which like our muscles can actually manipulate things. So tendons are connective tissues that attach muscles to bones. They also share, in common with ligaments, they do not get a lot of blood flow, and therefore they do not repair very quickly. When you hear about an athlete, tearing a muscle or, pulling a muscle or something like that, it is almost always a tendon's fault. Your muscles are pretty squishy. They're pretty good at contracting and relaxing. But if the tendon does not relax, that means that like that muscle has to like extend over a much longer distance. And so that's why tendinitises are so common. That's why muscle pulls are so common. They just don't repair. Again, tendons attach muscles to bones. Ligaments attach bones to other bones, okay? Now, let's look at our muscle fibers. Let's look inside of a muscle cell. We looked inside of a neuron earlier. Well, let's look inside of a muscle cell. So one of the other really big things that they want to test you on, they love to ask questions about this, is the microanatomy of what's going on inside of muscle cells, right? So like I said, you're going to see all the normal stuff inside of a cell. You're going to see fluid in every single muscle cell. Normally we call cell fluid, we call it cytoplasm, but because we're talking about muscles here, and muscles are like the fleshiest parts of our body, it gets a special name. We call it the sarcoplasm. Sarco means flesh in Latin. And so sarcoplasm is flesh fluid, which, don't think too much about that. But and then within there, you're going to see some glycogen, you can see some fats, minerals, things like that. That's your sarcoplasm. You're also going to see nuclei, lots of little nucleuses running throughout. Nucleus, kind of like the brain of our cells that are, contains all of our DNA. Your muscle cells have a ton of nuclei in them because the nucleus is what contains your blueprints, and muscles are really good at growing. And so thanks to having all these nucleuses, the more nuclei that you have, the more likely it is that your muscles are really good at experiencing growth. And that's one of the reasons why, again, exercise translates into muscular growth. And then you can see mitochondria. Mitochondria, the little powerhouses of the cell, they're taking chemical energy and turning it into energy for the cell to keep your cells alive. But again, the unique thing within muscle cells is that they have these specialized proteins called myofibrils, okay? So myofibrils are special proteins that run end to end within our muscle cell. They're like a rod that runs through the entire length of our muscle cells. And that rod has all these little proteins in it. Now, this is where we get really technical here, but within those myofibrils, you're going to see these proteins. These proteins, we're going to call these myofilaments. And so you can see different myofilaments here. You can see these little thin strands here. There's 3 of them, right? And you see these 2 really thick strands with all these weird Dr. Seuss looking heads that are kind of branching out from there, right? So those thin strands, they're strands of binding sites. This thin strand is a protein that is known as actin. Actin is this thin little filament that has all these little like binding sites available, right? These little dents. And then you've got myosin, which is that thick filament with all the heads. Those heads like to reach up and grab those binding sites. And so when that happens, what will happen here? I'm going to actually, where the heck is my button? There it is. should have moved that before I started. Okay, take a look right here. If we look at like, there's our little thin filaments and there's our thick filaments. Well, what's going to happen is these heads are going to reach up and they're going to pull towards its center right here. Okay, and so what's going to happen is it's going to pull this way, and then the other fibers are going to pull this way. And so the entire sort of area where this is happening is known as a sarcomere. It's the area of town, basically, where actin and myosin are overlapping with one another. And so the sarcomere is going to pull, and there's going to be kind of this sliding action. Like those little heads are going to kind of crawl like this. In fact, if we actually look at like actin and myosin here in action, if we look at a little GIF, they literally kind of crawl along like this. It's like a freaking Muppet, right? Like it's just kind of marching along. Here's that little thin strand, and then here's that giant head that's reaching out and grabbing, and it's just kind of crawling its way along. So if it's crawling, the whole sarcomere is going to shorten, right? And it's going to slide like this. And the whole thing is going to kind of crawl its way towards the middle. And that sarcomere is going to shorten. So a myofibril is a whole bunch of sarcomeres lined up end to end. And they all shorten at the exact same time, which when that happens, that's going to drag the muscle cell from this side and drag from this side. And the whole muscle cell is going to come towards its center, and it's going to shorten. So those are our proteins there, right? That's a sarcomere, which is the functional unit of the nervous system. This is the area where this sliding action is occurring, and it's where myosin is grabbing actin. Now, we need to be able to relax our muscles as well. We don't always want this to happen. These proteins are always attracted to one another. They just want to bind, and they don't want to let go ever. So how the heck do we regulate that? How do we relax our muscles? Well, you have some proteins that live on the actin strand called troponin and tropomyosin. And they're regulatory proteins. They basically live on the strand, and they're there to block those binding sites. So you can actually see here, well, that's kind of disappeared, but yeah, okay. So it's kind of showing you where this contraction is going to happen. There we go. There's the sliding. We see that little, oh my God, too fast. All right. Come on, internet. There we go. There's this strand right here, right? Those strands are blocking the binding sites. But if those strands move out of the way and the binding sites are exposed, the muscle will contract. So when we actually are contracting our muscles, what we're actually doing is we're just moving those, moving this little strand out of the way, allowing that contraction to occur. How do we move that out of the way? Well, we actually use a little bit of calcium. You wouldn't think that, when we think of calcium, you usually think of your bones, right? But calcium is actually very attracted to this little protein called troponin. And that's the little green one right here. And so when calcium, if I flushed a bunch of calcium into this area, this little green guy would move towards that calcium. It's like it can't resist it. So it just moves away. And when it does it, it's attached to these little strands. And so the strands move away. And now the binding sites are exposed. And those little proteins are like, it is on, and they contract together. That's why if you're ever cramping up and you go to the ER, they will sometimes test your blood calcium levels rather than just testing your sodium and your potassium levels. A lot of times when you're cramping up, it's like, oh, go eat a banana. That's true if the problem is in your nervous system. Your nervous system uses sodium and potassium to kind of communicate, right? But if it's, if you eat a banana and nothing's happening, you're still cramping up, it could be because your muscles are contracting when they're not supposed to. And there might be like too much calcium in your blood, or, maybe not enough calcium in your blood. And so, we can't move that stuff around. And by the way, the area between a sarcomere, this is kind of in an awkward place here, but the area where the sarcomere is kind of overlapping, that area is called a Z-line. And it's where two Z-lines are moving together. So the reason it's called a Z-line is because if you look at the way these sarcomeres are all arranged, like this sarcomere on the right is straddling the one on the left. See how they, they don't line up perfectly? That's on purpose. And that makes sort of the zigzag pattern. And so that's why we call it a Z line. So every sarcomere has a Z line on both ends. And those two Z lines are basically being drawn together, right? So this one's pulling this way, this one's pulling this way, right? Both of them are sort of shortening at the same time. Okay, so let's take a look at like how, so that's what's going on in all of our muscles, right? That's what's going on in every muscle that you have got, is this constant like shortening and this constant like relaxing back to full length. So how does our nervous system sort of interact with all those muscles? Well, that is where we have to talk about how neural activation works. So neural activation is describing how your nervous system zaps and makes your muscular system actually contract. And it does this through the use of motor units. A motor unit is a neuron and all the muscle cells that it innervates. So you can actually kind of see in this picture here, the neuron's going to kind of run down and then see how it kind of branches out. Well, that's because it's going to zap several muscle fibers simultaneously. So if we look at a motor unit, it's kind of like a general and all of his troops, right? You can see if we looked at it right here, right? This is one neuron, and then it branches out and it zaps this fiber, and then it branches out over here and zaps this fiber, and it branches out over here and zaps this fiber. All four of those muscle cells are being zapped by this motor unit. Okay, so one of the ways that we determine like how strong of a contraction we make is we recruit either large or small motor units, right? There's a small motor unit over here, recruits 3 little fibers. There's a medium motor unit over here, 1, 2, 3, 4, 5, 6 fibers. And then over here, this is recruiting 9 fibers, right? So this is a large motor unit. Maybe this is like a squat, right? And this is a small motor unit. Maybe that is, I don't know, walking, very gentle. And then, walking, running, sprinting, actually, that's a better analogy. So that's what a motor unit is. It's one neuron and all of the fibers that it is going to activate. So what happens when we are shortening those sarcomeres and lengthening them back to full length is this concept that we call the sliding filament model. And it's describing how our nervous system triggers our muscular system to contract all of those sarcomeres. And so the muscle is going to get shorter because the proteins, actin and myosin, are sliding across one another. It's literally kind of going like this and then relaxing back to full length. So that's the sliding filament theory or sliding filament model. And then this is describing right here, this big, long freaking wall of text is describing everything that happens. So I'm going to go through this one time. It's very technical. You don't necessarily have to have all of this like fully memorized, but understanding how it works is helpful to understand how contractions take place. So what will happen is a nerve impulse, we call that an action potential, is going to transmit from neuron to neuron to neuron to neuron until eventually it gets to the muscle cell. And so then there's going to be a connection between the nerve cell and the muscle cell. That connection is called the neuromuscular junction. And it will use this chemical called acetylcholine, which is a neurotransmitter, to work its way across the little gap between that connection. And it's going to bind to receptor sites on the muscle cell. Those receptor sites are going to trigger the physiologic action of flushing calcium into the muscle cell. And now because all that calcium is in there, troponin and tropomyosin are like, oh my gosh, and they're really attracted to that. So it moves up and goes to grab the calcium. That moving up action exposes the binding sites. And now myosin with its big heads are going to reach up and grab actin and slide it towards its center. Meanwhile, that's happening over there as well, and it's sliding this way. So now the whole myofibril and all the sarcomeres are all shortening simultaneously, and that sliding is going to happen. And this all takes a little bit of energy, a little bit of ATP. So your body's breaking that down and creating more of that. Eventually, it's going to flush all that calcium out of the air of the sarcomere there, and that will allow the chaperones to go back into place and your muscle will relax back to its original shape. And that is muscular contractions in a nutshell. Like I said, very technical, but it does come into play when we talk about, like, you know, working with our clients. If you are trying to develop maximal muscle, well, you should be recruiting as many muscle fibers simultaneously as possible. Or if you're maybe working for like stabilization, you are going to learn how to recruit those muscle fibers for extended periods of time. So we have different types of lifting that are going to develop different types of muscle. So before I move into our different types of muscle, any questions on that? Questions, comments, concerns? Cool. Feeling good, guys.
No, it makes sense.
Well, let's take a look at our muscle fiber types. So you're gonna have two primary categories here of muscles. I mean, obviously you got lots of different types of muscle running throughout your body, but we're going to characterize them based on how they look and how they perform. So you're going to have the difference between type 1 muscle fibers and type 2 muscle fibers. Type 1 muscle fibers are what we call slow twitch muscle fibers. Type 2 muscle fibers are what we call fast twitch muscle fibers. So type 1 fibers, the slow twitch ones, they have a lot of blood flow. There's a lot of capillaries running throughout them. There's a lot of mitochondria producing a lot of energy in them. They have a lot of myoglobin, which is carrying oxygen, which makes them better at using that energy and, you know, using the mitochondria. So really good at producing lots of energy, right? But they tend to be much smaller in size. So they're able to do like very long sustained contractions. They have a lot of endurance. They don't produce very much force because they're kind of small. But they're very slow to fatigue. When you think about like your rotator cuff, you think about like the muscles in your core, right? Or even just like the muscles that are in like your calf when you're walking. That's very much like slow twitch fibers that have like a lot of endurance, right? But we also have our fast twitch fibers. Fast twitch fibers, they don't have as much blood flow. They don't have as much capillaries. They don't have as much mitochondria. They don't have as much myoglobin. So they're not very good at producing massive amounts of energy for extended periods of time. They tend to be much larger in size though. And so that means that they have more proteins, which means they are able to produce more force. But they are kind of quick to fatigue. This is why you can run a marathon using your calves, but you only do, you know, so many push-ups. That's the difference between type 1 and type 2 muscle fibers. Now, obviously, you can develop your body to develop either more of these. You know, if we look at the difference between type, oh, what the heck? Hey. If we look at the two very different types of athletes here, come on, internet. Sprinter versus marathoner. There we go. Take a look at the two like differences here. There's a big difference in these like two people's body. Both of these are Olympic athletes, you know, but like you can see very, very thin muscles over here that are really good at producing lots of energy over a very long period. I mean, a marathon is literally hours, you know, but over here we can see this is more of an Olympic sprinter, right? And that is very much, you know, much more type 2 fibers, which are obviously like much larger. They have the same muscles, right? They just look a little bit different depending on like what that looks like, right? Here we go. This is great. What a good photo. Marathoners' thighs versus like freaking sprinters' thighs. It looks like a freaking bodybuilder. You know, or you look at like the difference between like triathletes. You know, which, you know, like there's still like a goodly amount of muscle here, but like an Olympic triathlete is, you know, a much shorter distance. Look at like an Ironman triathlete, which is like the freaking longest event in the freaking world. And it's going to be a lot leaner. You know, there's going to be a lot less muscle mass there. So you can absolutely train to develop either more type 1 fibers or more type 2 fibers. It just depends on what type of training you're doing. If you are doing exercises that involve some seriously heavy movements where you're recruiting lots of muscle fibers, that's going to develop your type 2 fibers. Versus like if you do like very low repetition or very high repetition, low intensity lifting, that's going to develop your more type 1 fibers. Now, just so we're being a little bit more specific, we do break type 2 fibers down into 2 categories as well. There's the difference between type 2A and type 2B, which they started calling type 2X a couple years ago. But type 2A fibers are fast twitch, sort of, but like semi-oxidative fibers. So they're semi-slow twitch in that they get a little bit more oxygen delivery. So they're a little bit better at producing energy. They're not as good at producing energy as type 1 fibers. But they still are, you know, they're kind of like in the middle, right? They're fast twitch fibers. They're big, make no mistake, but they do have a little bit of endurance. When you think about like sports, when you think about like, you know, NBA players, baseball players, basketball players, which are NBA players, football players, like whatever. Generally, you're thinking of like type 2A athletes, you know? Like a wide receiver is a really good example. It's somebody who's extremely explosive, extremely fast, but they still have like a good amount of like big muscle fibers. You know, they're not going to be as fast as like an Olympic sprinter, but they're, you know, like DK Metcalf. He tried to like, you know, he tried to like Olympic sprint, right? He tried to do the 100-meter dash. And he is super fast, make no mistake about it.
Yeah, I see that.
But he's not like a type 2X athlete because the sport he's been playing requires like, you know, like a sprinter, they sprint for 9 seconds and then it's over. Their whole sport is done. You know, in NFL, you got to play all the minutes, you know, you got to keep going over and over and over again. So those are very different types of training. And that's the difference between type 2A fibers, which are usually for most sports that we're thinking of, very valuable. And then there's type 2X, which is the true fast twitch fibers. These are super explosive, and then they need to take a 20-year nap. You know, like, and that's where, like, you know, you look at like Olympic sprinter training. It's so funny. Their workouts will literally be like sprint for, you know, 9-10 seconds, and then recover for like 8 or 9 minutes. And then do a second rep afterwards. And it's like, what in a very, you know, but that's ensuring that they're good to go every single time. They're training specifically for their event. And then marathoners, it's like, all right, well, start running and we'll see you in 2-3 hours, you know? Very, very, very different types of muscle fibers. Last little bit on muscles here. If we are looking at how we organize our muscles, whenever we're talking about human movement, one thing that we need to remember is that muscles can only pull. It's the only thing they can do. I know we have an exercise, we literally call it the push-up, but even that is a pulling action. Muscles only pull, they can't push. The sarcomeres can shorten and then they can relax back to full length, but they can't push in the opposite direction. So because of that, we need to have this arrangement that allows us to move in both directions. So we are going to have what is called an agonist-antagonist relationship. If I need to be able to like move my arm this way, well, this muscle right here is going to shorten to do that. Meanwhile, the muscle that's on the opposite side is going to relax to allow that to happen. So this is now at full length and this is at minimal length. And then if I need to go the other way, well, now this is at minimal length and this is at full length. They are antagonists to one another. Every muscle in your body can be an agonist one moment. It can be the main muscle that we're talking about for whatever movement, and it can be an antagonist the next minute. It'll be the opposite muscle of whatever movement. Every muscle can be an agonist. Every muscle can be an antagonist, or sometimes it'll be a synergist. Synergist is a helper muscle that assists with a prime mover. So your gluteus maximus, that is mostly in charge of hip extension. It's the main muscle that does hip extension. So when we look at hip extension, which is, you know, literally coming up from the bottom of a squat. Okay, she's not squatting, but she's doing a kickback, right? She is extending her hip out this way. The glute is mostly in charge of that. Meanwhile, it is being helped by the hamstrings back here. The hamstrings are synergists during hip extension, right? Here's another really good example of hip extension, right? The glute is mostly doing most of the work, but the hamstrings are there to help. So in this example, the agonist would be the gluteus maximus. The synergist would be the hamstrings. And the antagonist would be on the opposite side, right? We have hip flexors on this side of the bone. And the hip flexors do the exact opposite. Like when she's going down towards the ground and her thighs are coming up towards this way, that's hip extension, right? I'm sorry, hip flexion. So now here we have hip flexion, right? That's hip flexion, and then she's also doing knee extension. But you know, those are total opposites of each other. They are moving in exactly the opposite direction. So that's antagonist, right? And then there are stabilizers running throughout the body, which are really just there to make sure that your body doesn't fall out of alignment. You know, your rotator cuff, your core muscles, all the stuff that's going to kind of keep you upright while you are doing these big, heavy movements. So think of an agonist as the main character in whatever story, right? It's Batman, right? He's responsible for whatever it is that we are describing. He's getting help from Robin, who's there to assist, and he's being antagonized by the Joker, who's doing exactly the opposite. And then everybody's being, you know, emotionally stabilized thanks to Alfred the Butler. So that is sort of how our muscles are going to work. Now, when we get to our kinesiology class next module, we're going to need to know which muscles are agonists one moment and which muscles are antagonists another, because that arrangement helps us understand which muscles we need to strengthen and which muscles we need to stretch. Let's say you get a client who has an anterior pelvic tilt, right? They have that Instagram booty. You know, we call this lower cross syndrome. But you see somebody who's got posture. Actually, here's a really good example of two different types of posture, right? We can see here, she's got an anterior pelvic tilt and she's got rounded shoulders, right? So what's happening here is muscles in the low back up here are overactive. They are way tighter than they should be. And so they are pulling the back this way. As an agonist, we need to make that muscle relax, because the antagonist on this side, her core muscles, are not strong enough. This has become overactive. So we're going to stretch this out and we're going to strengthen the core. She's going to do some planks and some low back stretches. Meanwhile, on down below, her hip flexors here on the front are pulling down like this. And that's why this sort of rotation's happening. You can even see, right? I got a little bit too much of this. And then her glute muscles back here are not strong enough. They are not contracting as much as they're supposed to. Same thing's happening up top, right? The neck muscles in the front are pulling more than they should. The upper back muscles down below are not pulling enough. Meanwhile, her chest muscles are pulling too much, and her muscles back here are also not pulling enough. So we need to, you know, contract to get her back to neutral. We know which muscles are overactive. We know which muscles are underactive, right? And if we can do the exact opposite of what our client is good at, that will draw them from this bad position, which is going to cause back problems, back to this neutral position here. So anyway, that's what we're going to talk about next mod when we get to kinesiology and stuff. All right, we're going to wrap things up today by talking about the endocrine system. So this is also a control system, but like I said, you can see NASM. I mean, we only got a little bit of notes here. There's not a ton of information in your book about the endocrine system, just because it's not something that we directly affect. I mean, exercise does absolutely produce testosterone and growth hormone and estrogen and things like that. It creates all these really positive hormones, but kind of in an indirect way. You know, we're not really training your endocrine system. So because of that, they kind of keep it brief here. And it's not officially part of the kinetic chain either. It's just sort of working with the nervous system to have certain physiologic effects on the body. So your endocrine system is a series of glands that secrete hormones to control certain bodily functions, right? So your pituitary gland, which is the master gland, is living right at the base of the brain there. And it's got, an anterior lobe and a posterior lobe here. But it lives right here. That's going to create initial hormones that will activate the rest of your endocrine system. So your pituitary gland might make, for instance, what's called thyroid stimulating hormone, or TSH. And that's going to run through your bloodstream. And then all of a sudden it's going to interact with your thyroid right here to release thyroid hormone. And thyroid hormone is going to tell your cells to either speed up or slow down, and that's why you'll sometimes hear people who have thyroid problems will also struggle with their weight. They just don't burn very many calories because their whole metabolism is just running a little bit slower. You've got adrenal glands, which are living on top of your kidneys. Well, your pituitary gland creates this stuff called adrenocorticotropic hormone, which is going to stimulate those. So your pituitary gland is the master gland because it secretes the juices that activate the other glands, which release other types of hormones. So adrenal glands, those are the ones that are responsible for like your fight or flight hormones. One of those is epinephrine, which we more commonly, this is actually synthesizing what we call it adrenaline. And those live on top of your kidneys. You've got your testes, which are producing testosterone in men. Women producing it in their ovaries, right? That's producing like our sex hormones, right? Men and women both produce testosterone and estrogen, but in obviously very, very different levels. Testosterone happens to be a very anabolic hormone, which does cause the growth of muscle tissue very extensively. And that's why we see higher bone density, we see higher muscle density in like male subjects versus women who produce some testosterone, but not nearly as much. And so because of that, muscle growth is just not as common, which is why women don't need to worry about like bulking up, go lift heavy. And so those are, our sex hormones and stuff. There's also like, actually there's that. I got ahead of myself there. And then there's also like controlling your blood sugar. We need to have sugar in our blood so that we can produce energy because your cells eat sugar and spit out energy. And so your pancreas, which is this organ that produces this material called insulin, releases insulin into your blood, which drives that sugar out of your blood into your cells. And so insulin will lower your blood sugar because we want to have our blood sugar at normal levels. But if it gets too high, like we need to have blood sugar, but if it gets way too high, that sugar starts interrupting other physiologic processes. Your body can't do other stuff. So we need to produce insulin to, drive that sugar out of our blood and either turn it into glycogen and store it for later or convert it into fat and store it for later. But your pancreas also creates glucagon, which if you haven't eaten for a couple hours, like me today, I totally was only able to get my coffee. I didn't have my morning breakfast. So I'm real hungry right now. My body is releasing glucagon to keep my blood sugar levels at neutral, and that's breaking down glycogen and elevating my blood sugar levels, back to an appropriate level. So we do know that exercise does have an effect on our endocrine system. It produces epinephrine. Exercise is stress, like it's literally a stressful event. So your body thinks it's fighting bears, so it produces adrenaline, it produces epinephrine. That elevates your heart rate. It releases glucagon into your system so that your blood sugar levels come high so you can produce lots of energy. And it produces like things that open up your airways, In fact, actually, if anybody has like an inhaler, if anybody in here has like asthma and you have like an inhaler, has oftentimes they'll put like trace amounts of like epinephrine in your inhaler. And that is like a little bit of adrenaline, which opens up your airways and makes it easier to breathe. Exercise is a very good example of, if we go back to our nervous system from earlier, we talked about how we have the sympathetic part of our autonomic nervous system. That's the fight or flight version. Exercise is a response to that fight or flight, which is one of the reasons why it's important to cool down after you're done working out. It's really important to, walk for 10 minutes or so, just to bring your heart rate down slowly, because you are signaling to the body, hey, the stress is over. We are back to neutral. And so your body can get out of fight or flight mode and get into rest and digest mode. And so it will stop using all of your muscles and then start repairing them and getting them ready for, the next time you work out. So like I said, here's kind of a common list of our hormones, right? Testosterone produced by both men and women, estrogen produced by both men and women, just levels very different. Cortisol, that's a stress hormone. That's a very catabolic hormone. Cortisol is really good at burning muscle and building fat, which is great if you need to start burning less calories because you're stranded on a deserted island. But it's not so great if you're living a normal everyday life and you're trying to be healthy. We are trying to produce less cortisol. We got growth hormone, which is produced by your pituitary gland. That's a very anabolic agent that is responsible for growing human tissue. Thyroid hormone, which is controlling your metabolism. And exercising elevates all of these. Guys, you're going to produce more estrogen and more testosterone. Women, you're going to produce more estrogen and more testosterone. Everybody who exercises, you're going to produce some cortisol in response. You're going to produce growth hormone. You're going to produce thyroid hormone. All of these things are going to happen in response to exercise. So, summarizing everything up, that was a whole freaking bunch of information. That was 5 days summarized into one big PowerPoint there. That's your entire NASM chapter 2. But summarizing everything up, you've got your kinetic chain. That's your nervous system, your muscular system, and your skeletal system. The nervous system is controlling everything. Your skeletal system is this framework that needs to be manipulated, and your muscular system is going to manipulate that skeleton under the control of your nervous system. And I could just loop around and it's a circle, they're all working together. They're all linked together. And that is about it today. How y'all feeling?
Pretty good, man.
Love it.
I feel good. That was interesting.
Feeling good.
Awesome. Yeah, Gabriel, that's a lot for your first day. We really threw it at you hard. So guys, on Monday we are meeting in person at Sochi. We're gonna have 2 sessions, just like we have 2 sessions every day for class. That is that's a cute smiley face. That is going to be either 9 a.m. Or 6 p.m. That's when we're going to meet up. That'll give you an extra half hour to deal with traffic and stuff, so you can get up at the same time you normally do and drive to school. You don't have to come to both sessions, although you guys are always welcome to come to both sessions if you want to. But we're going to kind of practice a little bit of what we're talking about here. We're going to do a little bit of different types of nervous system activation. I want to have you guys lift some light, kind of wobbly exercises, but I also want to have you lift some heavier exercises so you can feel the differences of how your nervous system is going to work in very different ways. So that'll be kind of fun. And we can kind of tie it together to what we're talking about here. So that's our Monday session. We will also have our midterm on Monday. That's going to cover all the content from homework 1, which was on Tuesday, and homework 2, which was on Thursday. Gabriel, you're going to be exempt from that. It would be ridiculous to have you take a test on something you started literally 1 day earlier.
Right.
I'm not a monster, so I'm not going to do that to you. But we will have you get through those homeworks so that you can kind of take a look at them and get familiar with them. So I'm going to have you stick around here. I do want to show you how we do our homework and stuff. So Lorianne, Bay, if you guys don't got any questions, I'm going to go ahead and let you guys go. Let me kill the recording here.